So that gives me a lot of flexibility. But then you see these masks are much more complicated than the regular masks. So in a research laboratory, typically it's very difficult to actually go through the mask and fabricate them. So one of the techniques we use when we want to miniaturize these structures is what is known as electron beam lithography. Because in this case, I have shown you the splittering resonators, right? That was at 10 gigahertz. But I want to even make it at 1 terahertz, right? We showed this structure already in the negative index case. So 1 terahertz means maybe this structure is few microns in size. How do we fabricate structures which are few microns? If you have a typical electron beam, a typical photolithography, you can't do it. So we use another technique which is called as electron beam lithography. This is called Ebeam lithography or electron beam lithography. What it does is, now instead of using my light as a source, I use electron beam as a source. Okay, we know from de Broglie principle that electron has a certain wavelength associated with it. Given an energy, we can compute the wavelength, and then we can compute basically wavelength of the electron beam. How do we calculate the wavelength of electron beam? Let's say I have 100 eV, right? 100k eV electron. How do I compute the wavelength? Well, my momentum is simply going to be P is equal to square root of 2mE. So I can compute in terms of EV, you put that and then compute the momentum, and lambda is simply going to be h by p. I think we did the assignment. I think first week I had some questions on this direction, right? So you see that for a corresponding energy, the wavelength of an electron is going to be much smaller than the wavelength of the photon, right? But then of course electron beams are much more challenging to handle, because now if you want to move the electron beam, right, how will you move it? Essentially what you have to do is you have to put plates like this, and then you make an electron pass through that, and then try to adjust the voltages on this plate so that you move the electron beam back and forth, right? So that's a much harder problem. So the machines that can do it are quite sophisticated. One example of the machine I have shown here, wherein they actually use, I think, 30 keV electron beams, and we can write patterns. Okay, so you have an elaborate system where you have basically focusing optics for electrons. Focusing light is easy, put a lens, right? And electrons, we have to do a lot more stuff. We have to apply high voltages, we have to control the focusing, we have to control the zoom, and so on. So many things are available, but everything can be done in a certain fashion, but it's relatively more expensive piece of equipment. So once we have it, we can actually focus. Now once we have an electron beam, we can actually improve the resolution. What will we do? Now electron beam also is a high energy beam, so it can actually make wherever you expose it, it can actually the resist can become soft. So what if the resist becomes soft? Now can we, this is a technique that we have already done, right, where to fabricate the PCBs, right? How will we modify this to create a metamaterial like this? So what I want is, let's say, a substrate. On that I want to have gold, let's say gold splittering resonator like this. So let's say I want this substrate to be, let's say, glass, and this thing should be gold, and I want it to be small size. So maybe this is 1 micron gap. So if you have 1 micron gap, you cannot really use it. So what do we do? How do we improve this? How do we modify the process? Well, directly, right. So what do I start with? Photoresist? No, substrate. What sort of substrate should we start with? So you should start with a substrate of this form. Let's say glass, and then gold. Okay. If you can start like this, and then make mask on areas where you want the photoresist to remain, and then etch gold. But how do we etch gold? Gold, it turns out to be is very hard to etch. It's a noble metal. It's not that chemically reactive. Okay. So if you use wet etching, aqua regia is one solution which can etch gold, but it's not very easy to we cannot use an wet etching process, because we are talking of micron scale. The undercuts itself will be very large and it will spoil the dimension. So we have to use dry etching. The dry etching is not really that amenable for gold. Okay. So one of the simpler processes, I mean there are ways to do it, but one of the simpler processes of doing it is the opposite. Instead of doing an etch, you do a deposit process, which is opposite way of doing it. So what you do is, instead of this gold film, instead of starting with like that, take a glass substrate, and do a positive resist, right? So basically, let's say a positive resist like this. Wherever you want the gold to be there, you open the window. Basically that means you'll do the same process. You put a photoresist and then expose it to light, make it soft. In this case, it should be an Ebeam resist instead of a photoresist. You write with an Ebeam machine, you expose this. Wherever you expose now, you simply deposit metal. If you deposit metal, essentially what you will get is now, in this case, I'll have gold like this. Okay. So basically I'm depositing metal here. Okay. Once I deposit metal, how do I deposit metal? So every step in this case is we will use what is known as evaporation. One of the techniques is evaporation. There is sputtering. There are many techniques. Evaporation is one of the standard techniques. Okay. So let's say I'll talk about evaporation in a moment. But let's say we have managed to deposit gold. Then how do we make the structure? Now, if you deposit, you cannot controllably deposit in only one area. You will put it in a chamber where you deposit, evaporating. Okay. So we have to go through a process which is known as, what is the process? Lift off essentially. So I'm sorry, I should actually put gold here also. Okay. Once you do a lift off process, lift off means, let's say the photoresist is soluble in something. You put it in, let's say acetone. What happens is, wherever the resist is soluble, it just, resist will simply go away. Along with it, the gold also will go away. But wherever you directly exposed it, there the gold will stick to the substrate and it will not go away. Okay. So it's something like, let me see an example. You mask, let's say, you want to paint something, like spray paint. Let's say you want to spray paint a design or something. Well, in this case, what you can do is, you can cut out a paper in a shape and then do a spray painting. Wherever you don't want the paint, they'll have a paper, right? And then simply dissolve the paper and then you get left with a pattern. So spray painting, you're essentially depositing the color on the wall. Similar, just with some mask, right? So essentially, similarly, you can make a mask out of photoresist. You deposit everywhere, and then there you simply remove the paper by hand. Here you have to dissolve the paper. Again, putting water is enough to dissolve the paper out. So you are left with something which is solid. Okay. So that's a deposition step. So lift off process basically removes, in this case, wherever you have the gold, right? Lift off dissolves PR, leaving behind gold. Okay. So now because of that, at the end of it, you get basically a film like this. And then there's a gold pattern like this. So this is a cross section, but you can make a split ring resonator like this. So this is one of the ways to make a structure, what we have. And then you also can, I said, we'll talk about evaporation. It's not a simple process, because how do we evaporate? Question was, so you have said that shrinking the wavelength has been challenging, because I said 193 nanometers was where it is stuck for nearly 15 years, I think, 20 years also, I think. So they tried 157, it didn't work out. So finally now they have come to EUV, which is not at all power efficient. And it's a big bottleneck. So instead of using this, why don't we go to electron beam? That's a question, right? The problem with electron beam is it is a raster scan. Okay. For example, if you want to, let's say, I have a structure like this and I want to make a split ring out of it. Okay. If I use photolithography, I can put a mask and then one shot I can expose everything. It might be small, when I have small structure. But if the current generation technology has 12-inch wafers, 12-inch wafers, right? Over which we fabricate these structures. So if you want to fabricate over 12 inches, it can be done within a minute, all of it, parallel. But if you write with an Ebeam process, so this is basically photolithography. Is basically blanket exposure. Right? All over it, one shot. But electron beam lithography is basically raster scan. That means you are almost as if you are focusing an electron beam and writing it one location to another location. So it takes a long time to write. So if you want to write with an electron beam machine over a 12-inch wafer, God save you. It will take, I don't know, lifetimes. Okay. So what we do is typically, even in photolithography, we don't expose the entire wafer at one shot. We have what is known as a stepper. So expose a small die, keep moving, move like that. But it can flash. A wafer can be processed within a minute or something like that. So quite fast they can do it. But electron beam will take ages. So electron beam is useful as a research tool. But in production, you cannot do mass production with an electron beam machine. But an electron beam is still used when making the mask. You can do all these techniques, but mask also is required, right? Who makes the mask? With an electron beam machine. And that is why mask is actually very, very expensive to make. So I know that, the state of the art, let's say NVIDIA chips and things like that, the mask itself might cost about $40 to $50 million to make a mask set. It's quite expensive. So it's a very, companies actually have to think about a lot of cost and all that. Okay. So yeah, electron beam that way is okay as a research tool, but not a production tool. We can make masks, but not more than that. In fact, historically, there was a period in TSMC where they actually tried to do parallel electron beam writes. So instead of using a single electron beam, they said we'll put 10,000 electron beams and we'll move them parallelly so that we can write it faster. TSMC, in fact, I think actively pursued it. There was a Dutch company who tried to propose this and all that. But it didn't really pan out, I guess. You can also think why it won't pan out. To control one electron beam, we are buying a 5 crore equipment. If I want to control 10,000 beams, I don't know what we're going to do. And they're all going to interact with each other. It becomes much more challenging to control them. Right? So that's the tough part of controlling the electron beams. Well, they invested some time, but I think now eventually I think TSMC came down to EUV. Extreme UV has its own disadvantages because, we understand optics now very well, right? The refractive index. What is the extreme UV is 30 nanometers. What is the refractive index of glass at 30 nanometers? What is the transmission of glass at 30 nanometers? 30 nanometer light. What will be the transmission? What will be transmission through glass? How do we know? Glass is SiO2. So SiO2 band gap is 9 eV. What is the energy of the photon? E equal to 1.24 divided by 0.013. How much is that? Can somebody tell me? Let's say 1313, right? How much? 137 is close to 124, let's say. So it will be 1000 EV or something. Very large number. So if you have such highly energetic photon, it will get absorbed first of all. You can't use glass. Then how do you focus that photon? How much? 925, huh? 925. Huh? 95, okay, 100 keV. 100 keV. 100 EV. 100 EVs. That's it? Come on, man. 1240 divided by 13. Okay, 100 eV. Okay, fine, roughly. Okay, so 100 eV means it's a highly energetic photon. So glass will absorb. You can't focus the light. So how do we build lenses? How do we focus light? Extreme UV light. Nothing. Every material will absorb. Whatever traditional materials you have to put, diamond. Diamond is the hardest material. What's the band gap? 5, 6 eV? Absorb. Everything absorbs in UV. So what do we do? How do we lens? How do we focus? Reflective lenses. Think of reflective lenses. Traditional lenses are this fashion, right? The light is going like this and then that's getting focused. But now this thickness is, let's say, a few millimeters, or 10 millimeters, I don't know, lens thickness, millimeters, tens of millimeters maybe. If I put tens of millimeters of glass, UV will get absorbed. You cannot use this sort of lens. So we have to use reflective lenses. How do we make reflective lenses? Yeah, if I want to basically, instead of transmitting, I have to make it like go like this and then focus. Go like this and focus here. Okay, reflective lenses. Reflective lenses, what will reflect at that wavelength? Very highly absorbing material. What will reflect? Metals, in the case of IR, what do we say? Metals cannot penetrate inside. But because, here in this case, actually they penetrate and they get absorbed. So what will reflect? I talked about it multiple times. Anyway, multiple layers. Tungsten and tungsten, I think molybdenum. Tungsten and molybdenum. You make thin films of tungsten and molybdenum in a periodic fashion, like a 1D photonic crystal. You make the reflectivity go very high. Why tungsten and molybdenum? They're very, very hard. So they're not getting damaged. So you make a metal thin film out of it. Thin films, you make a reflective film, 1D photonic crystal. 1D PHC, right? You make a photonic crystal out of it and then you reflect light. At that wavelength, it cannot penetrate because it simply has a band gap. Did we give this problem in the first assignment? I said that, okay, if you have a wavelength of 30 nanometers, you can actually put multiple reflect. What is the periodicity with which we get, we can try this. Just pick up the refractive index of whatever. I'm not exactly certain if it is molybdenum and tungsten, but you can have two different materials. Let's say the A by lambda we know. What is the periodicity required to reflect 30 nanometer left? And let's assume that we have the same structure of A by lambda equal to, we have to compute some things, but we can think. Okay? Or, roughly at least we can give an idea. Of course it's going to be in what thickness range? It has to be thin. Because, remember always, this is, in a way, even your lattice, right? I'm sorry, I'm diverting a little bit. I hope that people will excuse me for this. But, you have silicon atoms, right? You have X-ray diffraction. What is X-ray diffraction? You have light incident and it's getting reflected. From all these, multiple reflections from each plane, they come back and then they add up in phase and you get diffraction, right? So, atomic lengths are angstroms. So, X-rays will get diffracted. So, you have to put nanometer scale. Maybe 5 nanometers or so, 10 nanometers. Huh? Oh, X-rays are very nice. X-rays, the problem is, okay, the question was, why can't you do X-rays for lithography? People have tried it. The problem is, how will you make X-rays interact? It just keeps going through, right? X-ray, if I put on the hand, only bones are able to stop it. X-rays do not interact sufficiently. The problem is we have to make the source sufficiently interact with the resist, right? So yeah, you can do a lot of things like this, okay? So basically you have, you can make a 1D photonic crystal and then you can actually, I'm sorry, am I running out of time? Huh? Sorry, I think maybe 52 minutes. Okay, I should stop this. Okay. Anyway, Yeah, I mean, we can, this is a very open subject. We can talk, and yeah, there's a lot of things that can be done. Anyway, so you see the ideas we have learned in this course are relevant in so many different directions. And that is, I think, in some way the beauty of nanophotonics. All right. So anyway, quickly, I'll just talk about my, this one. Okay. So physical vapor deposition, right? Evaporation. How do we evaporate metals? So one of the ways to do that is basically you have to essentially melt metal. Once you melt metal, you have the it comes into the atoms come into the system in the vacuum. They come out of the in the molten form, they escape and they come into the gas phase, and then they can get deposited. For example, one of the ways to do that is to create a very high vacuum chamber like this. So create a chamber which is at high vacuum, and then you heat basically using an electron beam. You put a metal here, okay, and in that you shine electron beams on that. When you shine electron beams, they heat it up. When they heat it up, the metal will melt, and then you have this gaseous phase metal which goes and deposits on a substrate. Okay, why do we need a high vacuum system? Because high vacuum makes it if you don't have high vacuum, the atoms, right? Let's say you're depositing aluminum. Aluminum will simply undergo Brownian motion, scatter everywhere, and go everywhere. They won't go in, this sort of straight lines, they not really be straight, but yeah, they go long distances. The mean free path is going to be large if you have high vacuum. So you create a high vacuum system wherein you put a electron beam and then melt it, and then you make it deposit, okay? And then we can monitor the thickness using things like quartz balance and things like that, all right? So this is one way of doing metal deposition, all right? And we can actually, optics is very, very central to all this, areas. If you want to even find out the thickness of materials, again, optics is very crucial, because in this case, again, let's say you have a sample, I want to find out the thickness. So there is a technique called as ellipsometry, wherein you measure the reflection coefficients of basically with different polarizations, P polarization, S polarization. You measure the reflection coefficients and you can compute, there are some ellipsometric parameters called psi and delta. You can measure them or you can compute them, and then you can try to fit your experimental data with your theory. Okay, we have understood all the Lorentz model, Drude model, and so on for the optical material parameters. So ellipsometry can actually help you measure these reflections. And then, in this graph, I just showed you an example of where the model and the data is exactly fitting. You measure these parameters in an ellipsometer, which is it's a very nice tool, beautiful, versatile tool to measure thin films, even down to 1 nanometer. You can measure. So you fit the data, and then you can compute, you can estimate what is the thickness. It's an indirect technique, but still it gives you very, very accurate data, because we are measuring it multiple wavelengths. We don't just do it one wavelength. We go, let's say, from 300 nanometers to 1000 nanometers. When we measure at multiple wavelengths and you're able to fit the exact physical model, that means that is the only solution that is available. Okay, so that way it's a very reliable tool that is used routinely in the semiconductor industry. So with that, I would like to stop this lecture. I know it went a little bit long. Maybe I'll try to split it into a couple of two parts or something. I'll post facto, I'll do it. So maybe I'll have to find a way, place. Anyway, so please bear with me. So I hope that, I have convinced you that optics plays a central role in a lot of different areas, and I have given you a glimpse of it through these lectures. So now in the next 4 weeks, I'll try to move forward from here and we'll talk about quantum optics. All right. So that's the plan. All right. So thank you so much for your attention. I'll see you in the next week. Bye.